Welcome to our explainer. I am absolutely thrilled to present this work straight from our team at the VITES lab, covering our paper, Adaptive and Stratified Subsampling for High-Dimensional Robust Estimation. Today, we're going to take a close look at a really fundamental bottleneck in modern statistical theory. You see, the big question is, how exactly do we process massive data sets, ones plagued with heavy-tailed noise, adversarial contamination, and temporal dependence, without totally drowning in computational costs? Well, we've developed some fascinating solutions to navigate these exact barriers, and I'm super excited to walk you through our structural frameworks and mathematical findings today. Here's a quick map of our intellectual journey. We'll start with the high-dimensional regression challenge, then introduce our proposed algorithms AIS and SS. After that, we'll hit our theoretical guarantees, explore how we combat contamination and dependence, and wrap up with the empirical results and runtimes. All right, diving right into section 1. The high-dimensional regression challenge, specifically navigating scenarios where P vastly outnumbers N. Now, the crucial question driving this entire research project was exactly this. How do we achieve robust estimation for massive datasets without suffering from a crushing computational bottleneck? Classical full sample gradient methods require an operational cost of big O of n times P per iteration. When you stop and think about it, as the number of samples, n, and the number of predictors, p, scale simultaneously into the millions or even billions, your memory and processing requirements don't just grow a little bit, they explode multiplicatively. That cost simply becomes impossible for any modern machine to handle. So subsampling, meaning replacing the full sample loss with a weighted subsample loss of a much smaller size m, well, that's the natural answer, right? But it brings some pretty severe statistical challenges along with it. We recognized early on that real-world data isn't perfectly behaved like it is in a textbook. It's chaotic. Classical subsampling methods work wonderfully under ideal, light-tailed, independent, and identically distributed data. But our models, they have to survive the real world. We're looking at scenarios where your predictors completely outnumber your samples. We're dealing with heavy-tailed, finite-variance noise. We have to handle adversarial epsilon contamination, which is basically when bad actors or broken sensors inject extreme outliers into your set. And we can't forget temporal dependence, or alpha mixing, which is incredibly common in time series data like finance or sensor networks. Transitioning from ideal math to this real-world chaos is exactly what we designed for. So, with that intense motivation established, let's jump into section 2, proposed algorithms, where we introduce our two novel mathematical solutions, AIS and SS. To really grasp how our methods work, we first need to define the bedrock they are built upon, the Huber loss. The beauty of the Huber loss is how it perfectly interpolates between quadratic laws for small residuals and linear laws for large ones. The exact transition point there is governed by a robustness parameter, tau. By tuning this parameter, your model behaves just like ordinary least squares for the well-behaved data right in the center, but then it transitions to absolute loss behavior at the tails. It's like a built-in shock absorber that cleverly ignores those extreme outliers. Both of our new algorithms strategically apply a subsampled version of this Huber lasso estimator. And this brings us to the stark, really fascinating contrast between our two proposed methods. On one hand, we have adaptive importance sampling, or AIS. AIS treats sampling as an iterative optimization step. It uses an adaptive soft reweighting process, constantly refining its probability distribution to hunt down and prioritize high-loss, potentially corrupted observations. On the other hand, stratified subsampling, or SS, is a non-iterative, hard stratification technique. It partitions your data based on distance to the median, fits estimators on proportional subsamples inside each stratum, and then brilliantly combines them using geometric median aggregation. So AIS zeroes in adaptively, while SS uses structural partitioning for raw speed. Practically speaking, you choose iterative AIS when you suspect malicious corruption that needs active suppression, but you deploy non-iterative SS when your main constraint is sheer computational speed on massive, relatively clean datasets. Moving right along to section 3, theoretical guarantees and optimality, because theory and algorithm design absolutely must walk hand in hand here. Okay, this is the big one. The crucial point we mathematically proved is this minimax-optimal rate. We established that a subsample size of m achieves an error bound of big O of the square root of s log p divided by m. This is massive for us. It proves that statistical optimality is fully preserved even when you are aggressively subsampling. You're getting the exact same statistical convergence rate as the full sample Huber lasso, but it's entirely governed by your much smaller computational sample size m. From a computational standpoint, this essentially breaks the curse of dimensionality. Now, this powerful guarantee doesn't just float in a vacuum. It relies firmly on 4 explicit assumptions. First, a sub-Gaussian design matrix, which ensures concentration of the design.
Second, a restricted eigenvalue condition, ensuring the sparse regression is locally strongly convex. Third, finite variance noise, which is actually strictly weaker than the typical sub-Gaussian noise assumption, giving us way more flexibility in the real world. And finally, bounded sampling probabilities. Satisfying these 4 pillars guarantees our uniform score bounds and restricted strong convexity remain perfectly controlled throughout the whole process.
But hey, point estimation is only half the battle, right? As researchers, we need absolute confidence in our inferences. Because our estimator uses L1 regularization, it naturally introduces a shrinkage bias. It systematically pulls coefficients towards 0. To fix this, we formulated a nodwise lasso precision estimator. This applies a clever one-step Newton correction that essentially strips away that regularization bias to the first order. The math works out beautifully, giving you fully specified, de-biased, coordinate-wise confidence intervals. So your inferences are actually statistically valid, even when you're operating in massively high dimensions. Next up is Section 4, Combating Contamination and Dependence, where we look at how these estimators handle some seriously tricky non-ideal regimes. So how do we handle dependent time series data where consecutive observations are highly correlated? Well, we implemented a strict calendar time block protocol. Think about it. If you blindly sample a time series, you might pick adjacent points, completely destroying any assumption of independence. Instead, we draw block start times, retain the calendar indices for a specific block, and then explicitly discard a predefined temporal gap between those blocks. Enforcing that buffer zone guarantees temporal separation. This allows us to use Burby-U coupling to treat the retained blocks as if they were approximately independent.
And what about adversarial contamination? Well, our AIS algorithm acts like a shield here. In corrupted datasets, your error splits into a statistical term and an irreducible bias that's proportional to your contamination fraction, epsilon. AIS actively fights this by adaptively soft reweighting and downweighting those corrupted observations. It organically shrinks that bias, and the best part is, it does this entirely without needing to know the exact contamination fraction in advance. That kind of adaptability is a total game changer for practical robustness.
All right, theory is great, but in our lab, we always say, we need to show the receipts. Let's hit Section 5, Empirical Results and Runtimes. Check out the trends here. Notice how our AIS method drastically flattens the error curve compared to uniform Huber-Lasso under severe contamination. As the contamination fraction scales up from 0 to 20%, the uniform sampling error just absolutely skyrockets. It's off the charts. Our AIS method, though, keeps that estimation error tightly controlled. It successfully absorbs the shock of those outliers, explicitly validating our theoretical bound on the irreducible epsilon bias. To really put that into perspective, let's highlight this specific number. Our AIS algorithm achieved an incredible 3.1 times lower error than uniform subsampling at that 20% contamination rate. While uniform Huber-Lasso error grew by a massive factor of 7.6x, AIS only grew by 2.3x. That right there is the undeniable power of adaptive soft reweighting, protecting your estimator when a fifth of your dataset is quite literally working against you. Now, comparing the test mean squared error directly to runtime performance reveals the ultimate practical trade-off. AIS absolutely dominates in aggressively reducing the test MSE, tracking our theoretical convergence rate beautifully. But when you put them on the clock, Stratified Subsampling, SS, is unequivocally the fastest algorithm. See, AIS has this overhead cost of updating weights every single iteration, making it slower per call. SS just does one pass for distance, then solves it incredibly fast. Bottom line, if you have contamination and need precision, AIS is your champion. If your data is clean and you just need raw speed to chew through petabytes of info, SS is the clear winner. Speaking of real-world applications, let's talk about our results on genomics data. Our AIS method secured a 29.5% lower test mean squared error on the heavily high-dimensional riboflavin dataset, and this dataset is notoriously extreme. The full sample size N is only 71, but the dimension P is 4088. Despite that, using a subsample size of just M equals 22, AIS expertly navigated this extreme regularization pressure. Extracting meaningful signals when you literally have thousands more predictors than actual samples just proves its immense statistical efficiency out in the wild. To wrap up this explainer, we really want to leave the academic community with a thought for the future. The framework we've built opens a lot of natural research doors, but this is the one we're most excited about. How can we perfectly extend these geometric median aggregation techniques into federated learning environments? Just imagine running our stratified subsampling locally on distributed nodes and then using geometric median aggregation across the network.
You could drastically cut down on those expensive communication costs while maintaining absolute robustness against poisoned nodes. We firmly believe that is exactly where the future of this research is heading. Thank you so much for joining us for this deep dive.